Hi, everybody. This is one from 2008. We got a 70 kilogram woman and her 35 kilogram son are standing at rest on an ice rink as shown above. They push against each other for a time of 0.6 seconds. That's probably important, causing them to glide apart. The speed of the woman immediately after they separate is 0.55 meters per second. Assume that during the push, friction is negligible compared with other forces that they're exerting on each other. So in other words, no outside forces. And if we have no outside forces, then momentum is conserved. That's the big thing there. All right, so now let's figure out the first question that they have here, which is it says, calculate the initial speed of the sun after the push. So the first thing we realize, as we just said there, that the momentum of the system beforehand is equal to the momentum of the system afterwards because there's no outside forces and momentum is conserved. And by the way, the momentum of the system beforehand, they're just standing there, is zero. So the momentum of the system afterwards is zero. So what we can say then, another way to think about conservation of momentum is that the change in momentum of the woman is equal to the change in momentum of the sun, but negative because she's going backwards. Although then again, they say speed, so they don't really care about positives or negatives, so we'll just get rid of that there. All right, so next thing, since the change in momentum of the woman is equal to the change in momentum of the sun, then we can write it like this. The mass of the woman times the change in velocity of the woman, although since she started at zero, we can just say the velocity of the woman. That's got to be equal to the mass of the sun times the change in velocity of the sun, although since he started at zero, we can just say the velocity of the sun there. All right, now, almost there for this part A here. So let's just start to fill in some numbers. The mass of the woman is 70 kilograms. It says her speed afterwards was 0.55 meters per second. And that's got to be equal to the mass of the sun, 35 kilograms, times his speed afterwards. Whoops, I really should have here too, maybe little tick marks right there and there to indicate speeds afterwards. Another way just to do this is proportional reasoning. The sun's got half of her mass. So in order to have the same momentum, he's got to have double the momentum there. And so 1.1 meters per second. Okay, so now it says calculate the magnitude of the average force exerted on the sun by the mother during the push here. So, and that would also be the sun on the mother because they are the same. So if we look at this, we can say that the change in momentum, let's say, of the woman is equal to the impulse on the woman, which is the force on the woman times the time that that force is exerted. And since change in momentum is mass times change in velocity, I'm going to divide that time down there. And that is equal to the force. So this was mass times change in velocity. We divide the time down there. So next part, let's plug in numbers for F, so that, or not for F, for everything else, so we can solve for F. So the mass of the woman is 70 kilograms, and her change in velocity was 0.55 meters per second. And the time that that push was exerted, they told us was 0.67 seconds. So if you solve for all of that, you will get 64 newtons there. Now, another way that you could do it, although it's not really another way, it's the same way, is you might have done it this way and say, oh, force is equal to mass times acceleration. And what is acceleration? Well, that's change in velocity over time. But you see, we're right back to where we were down here. So it's ultimately the same thing there. Okay, so next. And I sort of used the answer to C already in solving for part B. It says, how do the magnitude and direction of the average force exerted on the mother by the sun during the push compared with those of the average force exerted by the sun, on the sun by the mother? I cannot speak. So on the mother by the sun and on the sun by the mother. Here's the thing, they are the same. And why are they the same? According to Newton's third law. So for every action, there's an equal and opposite reaction. All right, so last part here. It says, after the initial push, the friction that the ice exerts cannot be considered negligible. The mother comes to a rest after moving a distance of 0.7 meters across the ice. If their coefficients of friction are the same, how far does the sun move after the push? Okay, so there's a lot of different ways you could do this. You could find out the forces or the accelerations, and because you got the initial speed and the distance, and from the accelerations you could figure out the forces, and then you could figure out the force of friction from there and the coefficient of friction. I'm gonna go the work energy theorem way. So I know that, let's say the woman's got a change in kinetic energy, and that's got to be equal to the work done on her. And so since change in kinetic energy is final minus initial, and the final is 0, I can say minus initial is equal to force, and there's only one force in the end acting on her because gravity and normal cancel out. That's the force of friction, times this distance that she slides, times the cosine of the angle between the two. So now let's plug in for each of these. So this will be kinetic energy, 1/2 times mass times her initial velocity squared. By the way, this initial velocity is her moving with 0.55 meters per second. It's not 0 anymore. It's after the push. The force of friction here is mu times normal force. And since she's on a level surface, the normal force will be mass times gravity times d. And it will be cosine of 180 degrees, which will give a negative out front there. Okay, a few things happen here if you look at this. One is this negative cancels with that negative, and this mass cancels with that mass. And so there's a couple ways that you can approach it from here. What most people will do is they'll start to plug in, and they'll say 1/2 and times the velocity, which is 0.55 meters per second squared, and that's equal to, and set up mu, gravity is 10 meters per second squared, and the distance she moved is 7 meters. And you can set this all up, solve for mu. That's the same mu for the kid. Run it again with the kid's mu plugged in and the kid's velocity, and figure out the distance that they go. And that's perfectly good. The way I tend to do it, though, is I tend to look at it like this. If I look at this equation back here, that half's just a constant. They have the same u, they have the same g, so we can just say that the initial velocity squared is proportional to the distance. We already know that the velocity of the sun is equal to twice the velocity of the woman. So if we put twice in there and square it, that will lead us to the distance of the sun is equal to 4 times the distance of the woman. And so therefore, since she moved 7 meters, 4 times 7 is 28 meters. Either way will get you there.